In previous units, we've shown that science always goes wherever the evidence leads it. This unit is no exception. In planetary evolution, we looked at patterns we find today between earthquakes, volcanoes, geography, and age of seafloor. We looked at patterns and evidence from the past. This reptile fossil found on separate continents, Africa and India. We looked at similar rock types found in South America and Africa, as well as another different kind of rock type on Africa and North America. Knowing these observations and finding these patterns is nice, but the real question becomes, plate tectonic theory explains that plates are sections of Earth's strong, rigid outer layer, the lithosphere, and these ride over the weaker asthenosphere. These plates are in motion and they continually change in shape and size. The largest plate, of course, is the Pacific Plate, and several plates include an entire continent plus a large area of the seafloor. We know from our study on the Hawaiian Emperor seamounts that these plates are moving in different directions. They change directions and they change speeds all the time. Today we look at how these plates are going to interact. Let's start by looking at more details for the layers of our Earth. The lithosphere, which includes the crust and the upper part of the mantle, and this upper part of the mantle is a hard part of the mantle, rides above the asthenosphere. The asthenosphere is below the lithosphere, a little weaker, softer part of the mantle. And below that, then, we have more of the mantle, but it becomes very hard. This hard part of the lower mantle due to pressure. It might be useful to use a model to help understand these layers, and the model we're going to use today is a cookie. A cookie. An Oreo cookie. In case you've never seen an Oreo cookie before, it looks something like this. You have the upper, harder cookie inside the creamy filling, and we're using here double stuffed creamy filling, and then of course the hard lower part of the cookie. There are three types of plate boundaries where plates interact. Divergent plate boundaries, convergent plate boundaries, and then the last one is called transform. We'll start with divergent. In divergent plate boundaries, we have two plates that move away from one another. As the plates move apart, asthenosphere rises and partially melts to form lava. New crust is formed as lava fills the gaps between the plates. This is what's known as an oceanic ridge if it happens in the mid-ocean. This is also called seafloor spreading. On land, the continents being torn apart form what's known as a rift valley. Shallow earthquakes are associated with divergent boundaries. Here's a short animation showing you seafloor spreading at divergent boundaries. Notice the rising magma filling the gap as these two plates move apart. In our cookie model, we see the creamy fillings coming up between the two plates as they separate. The best part about the cookie analogy, I get to eat them. In a transform boundary, we have two plates that are sliding side by side. Strain or tension builds as they move until they finally snap like a rubber band, and we get shallow but very strong earthquakes. We live, as you know, on a transform fault, the San Andreas Fault. Relative motion will be moving up, and then San Francisco on the North American plate will move down, we'll soon be neighbors with San Francisco. We can build a bridge, the Irvine to Frisco Bay Bridge. Most transform faults are found and associated with a mid-ocean ridge. As we see in this animation, the transform fault occurs when we have seafloor spreading. At a transform fault, no new lithosphere is created or destroyed. For the convergent plate boundaries, there are actually 3 different types depending upon which kind, either oceanic or continental plates, are colliding. But we have 2 plates that collide together, that move towards each other. That's what a convergent boundary is. In the ocean-continental convergence, denser oceanic slab sinks into the asthenosphere. As the plate descends, partial melting of mantle rock generates magma, which then rises up and forms volcanic mountains. We have both shallow and deep earthquakes associated with this convergent boundary. As one plate dives down below, this creates a subduction zone and forms a deep sea trench. This is the pink valleys that we looked at in our previous map activity. When this occurs, old seafloor gets destroyed as it becomes the magma for the volcanic mountains on the continent. In ocean-ocean convergence, one plate dives down below another. We form a deep sea trench at the subduction zone once again. We have deep and shallow earthquakes, and the magma forms volcanic islands then on the oceanic plate. In our continent-continent convergence, neither plate really slides down below the other. The crust is compressed, and this creates folded mountains as the plates buckle and rise. Very little volcanic activity occurs here, and we get shallow earthquakes. This animation shows you India, right here, as it moves up into Eurasia. The collision of these 2 continents produced the Himalayas. Here's a convergent boundary between ocean and continent. Once again, the oceanic plate diving down below. We see shallow and deep earthquakes, lava generating volcanic mountains on the continent. We notice the subduction zone, the deep sea trench where this plate dives down. Now imagine if you owned this island on this oceanic plate. Punished. And back to our cookie one last time. Can I get some milk?